Okay, so today we want to look at some just modeling problems. So again, the goal here is typically we're going to take the situation, we're going to try to set up some function. We're going to try to use function notation, will be helpful. Like, in this case, we'll try to look for v of x, a function for volume in terms of x, things like that. So let's just run through a few of these and see what we get. So it tells us that Kellogg's is designing a new box for Frosted Flakes. Marketing has already designed the logos for the box and requires that it must have the following proportions. Okay, its width must be 3 times its depth, and its height is 4 times its depth. Okay, so we have a box, right? So what do we know about a box? We can find the volume, right? The length times width times height. We can find the surface area if you wanted to. I don't think we do here, but we could, right? These are things we could do with a box. So first question we have here is to find a function that models the volume v in terms of its depth x. What we can do here is if you think back to your function notation, like usually when you think of function notation, you think of f of x, correct? Okay, where f is the name of the function and x tells you what the input is. Okay, we want to write a function here that models the volume v in terms of its depth x. So what I would do there for my very start is I would say volume as a function of x. That tells me v is going to be the name of the function, and that x is going to represent my input. Okay. Now, what do we know about the volume? Just tell me something you know about the volume of a box. Do we know the formula? Length times width times height. Now, this is not a bad place to start right here. Now, here's the problem, will show up right away. We have the volume as a function of x, so x is our variable, right? Volume's our output, is length times width times height. We want all the variables to be x's. Right now we have 3 different variables, so we have to address that. Okay, so that's where we're starting at. Our goal is to have a function for volume where x is our input variable. So let's think about what this information gives us, and I'm going to draw a box. About all I can draw is geometric shapes sometimes, right? So there we have a box. Now, I know that generally we call this the width. Let's see, maybe this the width and this the height, maybe that the length. Seem reasonable? Again, it's just sometimes it's nice to just have a label here to help you. And then we're told that its width must be 3 times its depth. Oh, I guess the units are kind of bizarre here, so it's depth. So it didn't use depth, but the smallest one's going to be right here, correct? This W would be the smallest measurement. Okay, and I'm going to go ahead and call that X. Here, let's call it. Let's maybe width, just to kind of match with their width and depth and height. So this would be W times D times H, which it really doesn't matter. We're just measuring those. But we don't know. The depth seems to be the smallest. It tells us right here we want to call the depth x. So d right here is going to be equal to x. Right, so that's going to deal with that. And then it tells us the width is 3 times the depth. Well, if the depth is x, what would the width have to be then? 3x. And then the height is 4 times the depth, so that would be 4x. So what we could do here is we could take each of these unknowns, w, d, and h, and we can replace them in terms of x. So we could say v of x is 3x times x times 4x. So our function v of x would be 12x cubed. So that would be our answer to part A. That is the function that models the volume volume v in terms of the depth, which is x. Okay, so our next 2 questions, now that we have this function written, what's the volume of the box when the depth is 2 inches? Well, remember depth we just said was x, correct? So I'm going to take the equation and I'm just going to find v of 2, right? Or 2 inches. Now notice here x is cubed, so it is going to become inches cubed, which is what we would expect for the volume of a box, right? It's a volume. So here we'll get 12 times 2 cubed, which is that 96 cubic inches? Right. So we go ahead and evaluate that. That's our answer. So But looking at this really in terms of importance of understanding and how to do this process, it's really the most important that you can get this function. Applying it's great, we're going to answer this particular question, but like we're really not designing a cereal box. This is a made up problem. Like, I'm sorry if you thought there was cereal. There is no cereal today. Just a theoretical problem about cereal. All right, and C tells us a family size box has a volume of 192 cubic inches. So you can see twice as big. What should the dimensions be? It is twice as big. Now, you guys know we don't double all the dimensions, right? That would cause a problem. You could investigate that. But what this will tell us here, so in this case, V of X is 192 cubic inches, right? So we can set up 192 equals 12x cubed. And we can divide by 12, which gives us 16. And then we have 16 equals x cubed. So we know that to get rid of a cube, we're going to cube root both sides. Now, remember with cube roots, we don't need a plus or minus sign because it's a cube, right? Cubes preserve the sign. And then we evaluate this and we get that about 2.52 inches would be equal to x in that case. So if the x dimension was about 2.5 inches, right, that would give us, and we kept this proportions, we would have a total volume of 192 cubic inches for our cereal. Okay, so for our second example, we have 120 feet of fencing, and we're going to build a garden. Okay. Our goal, and this is a very common thing when working with word problems, is you're going to try to find a maximum. Right? We're trying to find the maximum area. If you think back to your graphing calculators, what was one of our commands under calculate was maximum. So we'll be able to use that today if we want to on this problem. All right, we're going to assume the garden's rectangular. Okay, so write a function for the area of a garden. Okay, well, just first step here, we're making a rectangular garden, correct? We probably would say that it has a width and a length, correct? Seems pretty reasonable. Okay, so we could say area of the garden. Do you want to use that? We could use W and L, or we could turn one of them into X. It really doesn't matter. So maybe we'll do that. Let's maybe say X and L. So A is a function of X would be length times width, correct? So here's my first function. This is an area formula. I just did length times L times X, or you could have X times Y, or L times W. It's up to you. The letters are just placeholders. So now, this function is great. It does describe our area. It shows us the input variable is X. It uses X over here, which is what we want. But unfortunately, it has this L in here. We don't want the L in there. We want to replace L with X. So we need to find some other relationship where we can relate the length to X to L, is what we're looking for here. Well, if you get this far, right, notice we haven't used the one piece of information it gave us. So guess what we're going to use? That one piece of information that they gave us. Well, if you have to build a garden, the 120 is going to be the perimeter, correct? So you could take a look. Now again, we're interested in area, but this is a constraint on our problem. We have this 100. You know, if you could buy an unlimited amount of fence, there is no biggest garden you could ever build. You could just, I mean, it'd be kind of silly, right? So here we'll get 2x plus 2l equals 120. That's just the perimeter function, right? The two sides plus the other two sides is the amount of fence we're going to use. Now, I have this equation here, a of x equals L times x. I need to get rid of the L. I want to pull the L out and replace it with something in terms of x. So that means I want to take this equation and I want to solve it for L. So let's subtract 2x from both sides. Divide by 2, and we get L is going to be 60 minus x. So I'm going to take that. So L, again, is 60 minus x. So A of x equals 60 minus x times x. Or you could say 60x minus x squared. Really either way is fine here. If you leave it in this form, you can factor it really easy, and we have a 0 at 0 and a 0 at 60. Here, if you do it this way, you could graph the quadratic and solve it to do different things like that. But either way, we now have a function for the area of the garden. Right? So, and with this function, you can kind of, we could think about some silly cases sometimes might help. But if we used all the fencing on the length, so this was 60 and this was 60 and there was no width at all, that would be really silly, right? But that would be x is 0, right? And then, our length would be, using this equation, would be 60. So that would use all your fence, correct? And again, this is not an area function. Or I could look at area here too. If you did area here, it would just be 0, which is kind of pointless, right? Or if you had x was 10, then L would be 50, right? Because we know x and L are related. And then the area here would be 500. Or if you had 20 and 40, that would give you 800. So we can see there's lots, it's going to change. The area is going to change as we change x, correct? From a kind of trivial case where there is no x value to, things that are getting a little bit bigger there. So what we want to do here, what's the largest garden he can create, is we just want to we want to maximize the function, this a of x equals 60x minus x squared. Now, you could do that using your calculator, but this is a parabola that opens down, correct? Right? And we know that if a parabola opens down, so if you want to graph it, it's going to have a point at 0, 0 and a point at 60, 0, and it's going to open down. So I guess up at 30 is where it's going to have a maximum. But also, if you remember that the vertex is when x is equal to negative b over 2a. For a parabola, that's the vertex, which since we know this opens down, right, because x squared is negative, or you could even think of it as negative x squared plus 60x, we know that's going to be the maximum, our vertex there. So that'll give us negative 60 over 2 times negative 1, which will give us 30. So the vertex is where x is equal to 30. And then a of 30 is going to be, I hope I wrote that down, you plug it into this function and you get 900 square feet. So again, I would check that on your calculator. It's a nice thing to review that we can solve a parabola by finding its vertex. Well, not solve it, but we can answer the question by finding the vertex of the parabola. The last question, what are the dimensions of the largest garden? Well, we know that when x is 30, we have the largest garden, correct? Well, we know the other dimensions, so if this is 30, this would have to be 60 minus 30, which would be 30, right? So the dimensions of the largest garden are 30 feet by 30 feet. Right, so that would be our largest garden. So for our third example, we're working for Campbell's Soup this time, I guess. The account with Kellogg's is closed. So now we're Campbell's Soup. Okay, we want to make a soup can that contains 1 liter of soup. We know that a soup can is a cylinder. We know the surface area would be 2 pi r squared plus 2 pi rh. Here, remember pi in all of these is just a constant. Even though it's strange looking, we don't have to solve for pi. We know what pi is, we just plug the number in. And the volume is pi r squared times h, right? Just the area of the base times the height is what we do there. Now, a little bit of a trick here that's going to make it easier is when we're trying to find what are we trying to do? What is the minimum amount of aluminum needed, and what is the radius of the new can? So that's what we're looking for, right? So we're trying to find a way to have our liter of soup but use the least amount of aluminum. We want to find the dimensions that make the best shape soup can here. Now, we know that this 1 liter, that would be the volume of this soup can, correct? But liter is not, it's kind of a different measurement, right? Because we're going to be talking about centimeters or inches or something of radius, like some linear measurement, where this is a volume measurement. Now, if the volume measurement is cubic inches, it works fine, because then when you cube root it, you just get inches. But here, liter is a little bit different. I mean, I don't know how well you remember your sciencey stuff, but this is 1,000 milliliters, which doesn't really help, because that's still liters, still not a unit measurement, but it's also 1,000 cubic centimeters. So that's what we want to use it as, 1,000 cubic centimeters is a liter. Because now when we do the math, this will kind of get whittled down, and then we'll just be dealing with centimeters, which is good. We can measure radiuses, a radius in centimeters. All right, so our first thing is fill in the following unknowns in terms of R. Fill in the following unknowns in terms of R, radius, for each of the unknown values. So for the first one here, well, this is kind of redundant, but the radius is just R, correct? That's the variable we're using for that. Now, if we go to graph it in the calculator, which we will, we're going to swap that out and make it an X on our grapher. But let's use R here. And then it says we want to solve for the height in terms of R. So that means we're going to take one of these equations and we want to solve it to where we get H equals. Okay? And then once we do that, the only other variable should be the radius, or I guess we have the volume too. So in this case, since we actually do know the volume is 1,000 cubic centimeters, right? If we want to find a function for radius, or for height in terms of radius, if we look at this second equation, we want to solve for height, correct? We want it in terms of radius, so that stays a variable. Pi is a constant. We know 1,000 for our situation. So what we're going to do here is say 1,000 equals pi r squared h. And if we want to solve for h, we just divide by pi r squared. So we get 1,000 divided by pi r squared equals h. So that would be something that would help us here. We're going to need that here soon. And then lastly, what's the surface area in terms of R? So real quick, what we're doing here, and this might seem, and it does, our goal here is we're trying to minimize surface area, correct? So we need a function for surface area in terms of R. Like, that's our goal. If we can write that function, we can graph it on a calculator, we can use algebra to find where the minimum's at, all kinds of fun stuff. Okay, so this is probably where you would start. But if we want to find the surface area in terms of R, which is the radius, 2 pi r squared, that looks great, right? 2 and pi are numbers, r is the variable we wanted, plus 2 pi r h. 2 pi is fine, r is the variable we desired, but h is not, right? We need to get rid of h. That's why we did this here. So we kind of did it backwards. Like we found what we needed before we knew what we were looking for. But you see the idea here? So my goal was to get a surface area function with just one variable. We're choosing to use r. So that means I'm going to have to replace h with this fact that we have from right here. Notice that we use both equations, correct? Tends to be that way. So S of r is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Again, I just pulled out the h, replaced it with that equivalent fact there. Really a common thing that we'll do with word problems. Now I just want to simplify here. I see there's a pi in the numerator and a pi in the denominator. They'll cancel. I see there's an r in the numerator and r in the squared in the denominator, so one of those will cancel. So we'll get s of r is 2 pi r squared plus 2,000 r. So this would be what we were looking for. That's the surface area in terms of r, which is what we have here. And we know that it's in terms of r because the only variable on the right-hand side is r. Now if we compare it to this line, this is, we're looking for the surface area in terms of r, but we still have h in there, which is a variable. So we had to get rid of that, but now we have what we're actually looking for. Okay, so we wanted to go ahead and graph this using our calculators. So make sure if you haven't tried that, stop the video and try that. And again, you'll change it from x's to y, the r's into x's and all that good stuff. And s of y will be, or s of r will be y equals. But what I did is, in order to graph this, and I can't project my screen up here because we're using the video camera, but so I went ahead and typed this in as my function. Okay, now when I started, I probably, because I always tend to start, I probably did a standard window, which a way that we can write windows is that would be x goes from negative 10 to 10 and y goes from negative 10 to 10. Right? We're all familiar with that, or at least we should be, right? Now, but when you graph that, you get like, what do you get, like a line here or something? I mean, it doesn't show you anything. But let's think about what this is saying. These are our x values, correct? These are our potential numbers for the radius of the can. Can you have a negative radius? No. So right away, I don't want to bother going from negative 10 to 10. Let's go from, maybe we'll go from 0 to 20. Right? That's still not a very, but if you think about radiuses of cans, it's not going to be bigger than 20 centimeters. That would be a giant can, right? So that's probably even a little big. But if you go graph here, now if you graph that, it's just going to be a completely it's going to look even worse because there's nothing there. Okay, so what I would do now is we know that we have a reasonable x values, correct? Our domain is reasonable. So at this point, I would just go to trace and just move my cursor around. As you move your cursor around in the first quadrant there, you're going to get numbers like, 600, 800, 900. It kind of depends how far you go. But it tells us we need to go look higher, correct? So what I'm going to do then is change this is my y max. I need to make it bigger. Now here I said 0 to 20. The one I had on my calculator was from 0 to 15. It both shows the important behavior because now you'll see that this scoops down and comes back up. Looks kind of like a parabola, but it's not because it's some sort of rational function here because it's dividing by x. But you're going to get a graph that looks like this. So make sure that that's something that you're able to get.